All right. So in this chapter, we'll study motion. Okay. Now, the first couple of chapters, what we want to study is describe motion. So, for instance, eventually, this is our final goal. Let's say you have x, y, and z axis, and let's say a plane is flying or a bird is flying. We want to describe this motion. Okay? And describing a motion, what does it mean? What do you think it means?
How fast it goes?
All right. What else? That's not complete information. Okay, so technically, here's what it means. Describing a motion means the following. It's asking you, where is the object at all times? Okay. So what you want to know is the correct description, of the most useful description is the location of the particle or the position of the particle as a function of time. Okay. So when somebody is asking you to describe a motion, what they're asking you is the following. Here's the location. Okay, so I'm giving you in 3 dimensions. Okay. What they're asking you is, what is its x coordinate as a function of time? What is its y coordinate as a function of time? Okay. So when somebody asks you to describe a motion, what they're asking you for is these 3 functions. Okay. And we'll learn this over the next two or three chapters. Okay. In this chapter, we'll concentrate on 1 dimension. We'll just ask you for x as a function of time. Okay. All right, and the reason being, so when something moves like that, okay, the projection of this motion along the x-axis is given by that. The projection of that motion along the y-axis is given by that. The projection of this motion along the z-axis is given by that. Okay? And it turns out that you can make changes independently to these motions. Okay? So you can make changes to this motion without affecting these 2 motions. Okay? You can apply a force along the x-axis, and it won't change the motion along the y and z-axis. Okay? All right, anyway, we've settled on. So let's step back. When somebody asks you to describe a motion, what is it that they're asking you? They're asking you for this function, the position as a function of time. Okay? Given this motion, now you have a complete description of the motion, and you can calculate anything it is that you want to calculate about the motion. So let me show you an example. Okay. Now again, I'm showing you this in 3 dimensions. We'll build this over 2 or 3 chapters. Okay? So let's see an example. Okay, so let's say here is a motion. Okay, again, I'll write. Okay, so I just made up a motion. Okay. Well, actually, all right, it's fine. All right, so this is the x position as a function of time. Here's the y position as a function of time, and there's the z position function as z position as a function of time. So it's traveling upwards. Okay. Now, if I make this, all right, on 7, and I'll do another example. So what this is it's a spiral motion upward. Okay. And it's going in the z direction exponentially faster. Okay. All right, so there is a motion described. And a couple of things we'll be interested in is the velocity of the object at all times. And you'll learn that the velocity is the time derivative of the position vector. Okay. Have you guys done derivatives in your classes yet? Who doesn't know derivatives? Everybody knows derivatives? Okay. So this is dx by dt I plus dy by dt j plus dz by dt k. Okay. There is x as a function of time, and derivative of that would be 7 cosine t I plus derivative of this is minus sine t, so minus and derivative of that is 4 e to the power of okay. So the message is you have the position as a function of time, and you could calculate the velocity. The velocity was just the time derivative of the position as a function of time. Okay. Now the thing you'll be interested in is the acceleration of the object. And the acceleration is given by the time derivative of the velocity, which is the second derivative of the position vector. Okay. And you guys following this? Okay. The derivative of that is minus sine t I minus 5 cosine t j plus 16 e to the power 4 tk. All right. So, and that's generally about all we need. Okay. So in fact, so once you have the acceleration, and here's what we do backwards. Okay. So, for instance, let's say you want to go from here to there. Okay. So you want to go in a rocket from here to there. So this is what you want. To get this is what you need. Okay. Did you guys understand this? If you want this trajectory, you have to have an acceleration as a function of time like that. And this is the force you'll have to apply. Okay. So that's what Mr. Elon Musk is concerned about. Okay. Now, in his case, the mass changes as a function of time. Okay. So if you want this is what you need. Okay. All right. Again, so let's say this right now we're in this step. This is the motion. We are in the process of describing it. We are in the process of getting this function. Okay. And once you have this function, you can get from here. You can get the velocity as a function of time. You can get acceleration as a function of time. And those are two of the things that we are mainly interested in. Okay? All right. So, um, so in this lecture, we'll be studying motion in one dimension. Okay. Again, going back to our, what we are doing is we are building toward a description of motion in 3 dimensions. And the reason we are starting off with describing motion in 1 dimension is because the projection of this along the x-axis is given by that. The projection of this motion along the y-axis is given by that. And these motions are independent. So once you learn how to describe motion in 1 dimension, then you just, to get motion in 3 dimensions, you just add 2 more functions. Okay? All right. Here's one more thing in our description. Okay. So, I mean, in life we don't deal with point particles. So right now we are going to describe motion of an extended object like this. Okay. I'm drawing everything because I'm recording this for, okay. Every point on this object has the same velocity. Yep. So we can describe this as a point object. Yep. So that's the only kind of motion we'll be considering for now. When is every point not moving at the same velocity?
It's rotating?
When it's rotating, very good. Okay, so right now we are not considering objects that are rotating. Okay, so what is it that they do when they skid and stuff like that on a car? Drifting. So we are not doing drifting. Okay. All right. When drifting is involved, what happens? You need these 3 functions, and then you'll need another 3 functions. Okay. I'm just going to write them as angles. You'll need those 3 functions. So it just gets a little more complicated, a higher dimensional motion. So right now we won't drift. Okay. So what we're going to do is we're going to treat every point is moving at the same velocity, so we can treat this as a point object. Okay. So all right. Another thing you have to keep in mind is so we'll start off with dealing with 1D motion. Okay. Vectors are quantities that have magnitude and direction. Okay. In 1 dimension, so okay. In 3 dimensions, how many numbers do you need for vectors? 3. 1 for magnitude and 2 for direction. I'm sorry?
I said angles, but correct.
Yeah, 2 for direction. In 2 dimensions, how many numbers do you need to specify vectors? 2. Okay. So 1 for magnitude, 1 for direction. In 1 dimension, how many numbers do you need for? Okay, so it turns out that so in 1 dimensions, the vectors can only point in this direction or that direction. So what you can use is the sign tells you the direction. Okay? So you don't need a number for the direction, but the sign tells you the direction of the vector. Okay? All right, so now we've set up the groundwork. Let's start the lecture. Okay? So we are studying motion in 1 dimension. What we'll be interested in is describe. So let me show you an example of a motion. Okay, so here's a motion. So here's this car that starts off here and goes forward and then goes back like that. And we'll be interested in describing this motion. Okay, now any useful information is we want to know where the object is at all times. Okay? And this graph tells you that. Okay? So this is the position of the object, the x position as a function of time. So what is this graph telling you? At 0 seconds, the object is at 30 meters. There it is. Okay? At 10 seconds, it's at 50 meters. Okay, so at 10 seconds, it's roughly that. At 20 seconds, it's back at 40 meters, well, slightly less than 40 meters. At 30 seconds, it's there, and 40 seconds, it's there. Yeah. 50 seconds, it's there. Yeah. So this graph is completely describing the motion. Yeah. And you can get any information you want out of this graph. So if you wanted the velocity of the car at this time, what you do is you go to the graph, draw a tangent line. The slope of the tangent line is the velocity, which you learned the slope of the tangent line is the derivative. Yep. So, again, giving this graph is equivalent to giving the position as a function of time. And that's a complete description of the motion. And that's what we're interested in. Okay? All right. So we consider motion along a straight line. Forces cause change in motion. Forces change velocity. And we'll study that later. That's called dynamics. That subject is called dynamics. Okay. We consider motion of a particle, point objects, or objects that move like a point. That is, every part of the object has identical motion. We've already defined vectors and scalars. Vectors are quantities that have both magnitude and direction. Scalars are quantities that have only magnitude. These quantities, velocity, acceleration, displacement, they're all vectors. Speed, pressure, temperature, etc. are scalars. Okay. All right, so here's another motion. Here's an armadillo moving that way. Okay, so the position, so again, motion is giving you the position as a function of time. Now, to give the position, you have to use a coordinate system. The position is with reference to some coordinate system. Okay, so let's say if this armadillo is moving in this direction, we'll draw our coordinate system in that x-axis along that direction. There's the origin. Okay, so the armadillo starts off at -5 meters. At 0 seconds, it's at -5 meters. At 1 second, it's at -4 meters. Okay. That's an awfully fast armadillo. All right. So maybe it's... Anyway. So at 2 seconds, it's there and so on. So there, they've given you x as a function of time. That's a description of the motion. Okay. Mathematically, a motion of an object can be described by giving the position as a function of time. Yep. And once you have this function, you have a complete description of the motion. And once you have this, what are you interested in? You're interested in velocity, for instance, which is dx by dt. Then you're interested in acceleration of the object, dv by dt. And then if you get really good, then you sometimes are interested in time derivative of the acceleration, which is called a jerk. Okay? But then you have to work for Elon and stuff. Anyway, okay. All right. Now let me, before I go back to the slides, let me make one point. Okay, so let's say so this is a motion in one dimension. So here's a motion described. Okay, and how do I calculate the velocity? It's dx by dt. This is 15t squared plus 12t plus 7. Yeah. And how do I calculate the acceleration? The acceleration is dv by dt Okay. So here's what I want to point out. Okay. If the position as a function of time is a polynomial of degree n, okay, so the velocity is a polynomial of degree n minus 1, and the acceleration is a polynomial of degree n minus 2. Yeah? Okay. Now that should be sort of obvious, but anyway, just want to point that out. All right. So the first vector we'll describe as the displacement, and again, even though you'll learn this in the next chapter, I'll already start mentioning this. We'll do it in 3 dimensions and then come back, always specialize to 1 dimension. Okay, so let's say you go from, here's your initial point and you go along this path and there's your final point. So that's a bird flying. Okay, the displacement of the bird is a vector pointing from the initial point to the final point. Okay, so there's your initial vector. There's your final vector. And the displacement vector, which is written as delta r, change in r, is final minus initial. Okay? So change in any quantity is the final location minus the initial location. Okay, and you can see this if you bring this over there. So this is delta r. You see Ri initial plus delta r is Rf. And you can see that in the diagram. There is the initial vector, and there is the displacement vector. This vector plus this vector, that vector, is the final vector. Okay? All right, so the displacement vector is, again, just a vector pointing from the initial point to the final point. Now, this is sort of, it's a very gross number, gross quantity. Why is that? Because what is the displacement vector for this journey? It's the same. How many different journeys are there for which that is the displacement vector? An infinite. Okay? So it's giving you no details of the journey. Okay? So it's a very gross quantity. Of course, in 1 dimension, if you're traveling in 1 dimension, let's say this was your initial point and that's your final point, this is your displacement vector. Okay? All right. So let's look at this diagram. In this, okay, so time is developing that way. So this happened at a later time, and so on. Okay, so let's say this lady walks that way, starts from home, walks that way, and then walks back. What is our displacement vector for this journey? 0 vector. Okay. For this journey, that is the displacement vector. Okay. All right, so this is a vector quantity, and the displacement vector is the final position minus the initial position. Just like we defined over here. See, displacement is final position vector minus initial position vector. You know? Okay, distance is a scalar. Distance is the actual distance traveled. So for this journey, the displacement was 0, but the distance traveled was 1 kilometer. Okay. For this journey, the distance traveled was 1 plus 1.75, 2.75 kilometers. Okay. Again, distance and displacement don't give any details, so you can travel the same distance in many infinitely number of different paths. Okay? So it doesn't give you any details of the journey. All right, before I go over the slide, let's say A is a vector. Okay, what is 5 times A? What is that? Is it a, what kind of quantity is it? Is it a scalar or a vector? I'm sorry? It's a vector. Okay, so what did you do here? You multiplied a scalar to a vector and you just multiplied its magnitude by that, but it's a vector. Okay, so similarly, A divided by 4, that's a vector as well. Okay, all right, so here's what we're going to define. The next quantity we are defining is average velocity. Velocity is a vector. Average velocity is defined as displacement, which was a vector, divided by the time over which that happened. Time is a scalar. Okay, so this is a vector quantity. Okay. That was the reason for introducing that. Okay, so average velocity is again displacement over time. So if you went from here to there, there was the displacement. Okay, so, and I'm doing this in 3 dimensions. Okay, and so average velocity would be a vector that's pointing in the same direction as the displacement. The average velocity will point in the same direction as the displacement. Okay. Now, of course, you guys have had calculus, so this kind of stuff doesn't satisfy you. What you're interested in is the limit delta t going to 0 and this is called dx by dt. Okay. That's the time derivative of your position as with respect to time, and that is the slope of the tangent line. Okay. Average speed is defined as distance traveled divided by time over which that change happened. Okay. And again, we will be interested in instantaneous, so we'll be interested in instantaneous velocities and speed. Okay. So again, if this was a motion, so let's say here was a motion that's described that as position as a function of time. If you wanted to calculate the average velocity between these 2 instants, it's the slope of this line. That's the average velocity. Okay? But again, you want to make this interval smaller and smaller. You want the velocity in the limit that interval goes to 0. So here's a smaller interval, then it's the slope of that line. And in the limit this goes to 0, there's the instantaneous velocity. The instantaneous velocity is the velocity at this instant. Okay? And the instantaneous velocity at that instant is you go to the graph, draw a tangent line to your graph, and the instantaneous velocity is the slope of that line. Okay? So the slope of the tangent line is equal to dx by dt. Okay? Instantaneous speed is the magnitude of the instantaneous velocity. Okay, so that's the only time speed and velocity are related. Okay? Okay, when do you have an acceleration? When are you accelerating?
Change in speed.
Okay, try that again. I'm sorry? There you go. Okay. So, okay. Anytime I ask a question, what you want to do is you want to look at an equation. Okay. So, physics makes mathematics come alive. Okay. So here's acceleration. Okay. Anytime you have velocity changing, that's when you have acceleration. Okay. If the velocity does not change, you do not have acceleration. All right. So now there's the equation. And again, velocity velocity is a vector, change in velocity is a vector, this is a scalar, vector divided by a scalar is a vector, okay, and so on. All right, so let's make sure we understand it sort of intuitively and pictorially. Okay, so let me do, these are velocity vectors. All right, am I accelerating? No. See, I've given you velocities at different instances. The magnitude and direction are the same. Acceleration is 0. Yeah. Am I accelerating? Yes. The magnitude of the velocity is increasing. And when the magnitude is increasing, the acceleration is pointing in the same direction. Okay? So this is, you're speeding up in your car, and okay, so now your acceleration is in the opposite direction, okay? And so if this velocity was positive, this acceleration is negative. Okay? Okay, now I'm going in a circular road at constant speed. Let's say I'm going at 50 miles an hour. Am I accelerating? So velocity has magnitude and direction. The magnitude is not changing. You can change the velocity by changing the direction. The direction is changing. You are accelerating. Okay? So it turns out that when only the direction changes, when the magnitude doesn't change, but only the direction changes, the acceleration is perpendicular to the velocity. Okay, so let me write this down. All right. So now, and of course, I'm just giving you extreme examples. I gave you examples where just the magnitude was changing. I gave you examples of just when the direction was changing, and of course you can combine the two. Okay. And in life, if you want this motion, you have to have this acceleration. Okay, or if this motion is being described, there is this acceleration. And then you go looking for what is the force that is providing you that acceleration. Okay? And if you want that motion, then you have to provide that force. So for instance, here's the sun, and we did this problem earlier. The Earth is going around the sun at 30 kilometers a second. The speed of this Earth is not changing. And you just learned that if the Earth is going in a circular orbit, it has an acceleration. That's called the centripetal acceleration. And about a few chapters from now, you'll learn the magnitude of this acceleration. Is that? So what is providing the force? I'm sorry? The gravity of the sun. The sun's gravity on the Earth is providing you that force. Okay? This is the Earth. Here is the International Space Station. This diagram is not to scale. It's going at 8 kilometers a second. You know that now this is experiencing a centripetal acceleration. What is providing the force? I'm sorry? Earth's gravity. Okay. Here's a circular road. You're driving on the circular road at 30 meters per second. And now here's a side view of this thing. So you have a centripetal acceleration. There's the road. Okay. So there's the center of the road. And okay, so here's a cross section. In that diagram, the car is coming out of the paper. Okay. The acceleration is in this direction. What is providing the force? Think about that one. Yep. No, the turning of the wheel is no. That's propelling you forward. Very good. It's the static friction force between the tires that is providing that. Try taking an ice cube and throwing it on a circular path. You can't do that. Okay? So the friction force. Anyway, so the point is we'll look at objects going in circular orbits. We'll look at objects that have an acceleration, and then we look for where the force is coming from. Okay? All right. So when do you accelerate? Anytime your velocity changes. And you saw several examples of velocity changing. And of course, we are interested in instantaneous velocity, instantaneous acceleration. Instantaneous acceleration is dv by dt, the average acceleration in the limit delta t going to 0. Okay? And again, if you plot velocity as a function of time, so here's velocity as a function of time, the instantaneous acceleration is the slope of the tangent line. Okay? So the acceleration at 1 second is the slope of that line. The acceleration at 2 seconds is the slope of that line. Okay? And the acceleration at that. Okay? Okay, so you guys have seen the fundamental theorem of calculus. So integration and derivatives are inverses of each other. Okay, so what this fundamental theorem of calculus says, if you take the integral of a derivative, then the integral undid that, so to speak. Okay, and so this is ft2 minus ft1. Okay? So it's this function evaluated at the two endpoints. Okay, and we're going to use that. Okay, so for instance, so here's velocity is the derivative of that, of the position. Okay, so here's an equation. And now you can do the following. Well, so you have an equation, and in mathematics, this is great. Okay, you have an equation, and if you hit this guy with a hammer, you got to hit this guy with a hammer. Okay, so let's do the integral of that, and the integral of that. And also, you guys remember, so for a one variable function, for a one variable function, this integral had a geometric interpretation that was equal to the area under that curve. Okay? So, if you integrate velocity as a function of time between 2 points, if you have velocity and you integrate between these 2 points, that is equal to the area under the curve. But the left-hand side says, using the fundamental theorem of calculus, it's this guy, x evaluated at that point and x evaluated at this point, which is the displacement. So the displacement is equal to the area under that curve. Okay? So if you plot velocity as a function of time, the area under that curve is the displacement. Similarly, you can show that when you plot acceleration as a function of time, the area under that curve is the change in velocity between these two instants. And don't worry about it, you don't have to remember this. Okay. That's just a little thing that we are pointing out. Okay. All right. Now we'll come to some equations that you have to know that we'll use in solving problems. Okay. So again, before we do that, so here's a motion where the velocity is constant, the acceleration is 0. Okay. Here the magnitude of the velocity is increasing, so the acceleration is pointing in the same direction as the velocity vector. Here the magnitude of the velocity is decreasing, so the acceleration is pointing in the opposite direction. Okay. And of course we did here, so in all these three examples, only the magnitude is changing. The direction of the velocity is not changing. Okay. We already saw the more complicated case of the direction changing. Okay. Okay. So again, acceleration is the time rate of change of velocity. Okay. So here's a velocity that's linearly increasing. So v is, let's say, at plus b dv by dt. Constant would be c1. Okay, so if velocity is a linear function of time, acceleration is a constant. So for this velocity, that would be the acceleration. Okay. For this graph, initially the acceleration is constant and now the acceleration is 0. It would be this graph. Okay. For this graph, the slope is increasing, okay, and this happens to be a quadratic function, and so acceleration is linearly increasing with time. Okay. All right, most of the problems, most of the situations we'll consider will be constant accelerated motion. Okay. Now, in real life, it's very hard to maintain constant acceleration for any length of time. Okay. Here's an example you encounter in everyday life. This has a constant acceleration, a freely falling object. Okay. But this thing doesn't last too long. You go to the tallest building, and in a couple of seconds, you'll hit the ground. You know? So even that motion doesn't last too long. You can buy the most expensive sports car and you can probably maintain constant acceleration for maybe 2 seconds, 3 seconds. Okay. All right, but anyway, for $300, that's what we're going to consider. Okay. So we're going to study motion where the acceleration is constant. Okay. You already saw that in this case, the velocity will be a linear function of time, and the position will be a quadratic function of time. Okay? So that's what we'll study. So these are the 4 kinematic equations. Okay? These again, the kinematics is the study of motion, the description of motion. So these equations describe the motion for you. Okay? Remember, you wanted position as a function of time, There it is, the position as a function of time. Okay? So what this equation is giving you is the final position minus the initial position. The subscripts 0 tell you that they're the initial position. Okay, so that's the displacement. But anyway, this is position as a function of time. Okay? So when acceleration is constant, this displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Yep. And of course, if acceleration was 0, this term would be 0, and your displacement would just be your velocity times time. Yep. This tells you, again, displacement is average velocity times time. And when the acceleration is constant, the average velocity is equal to final velocity plus initial velocity divided by 2. It's just the average of those two guys. This equation gives you final velocity as a function of time. Okay, and again, when acceleration is constant, velocity is a linear function of time, and that's what this thing is telling you. Velocity is a linear function of time. Okay. What this equation gives you is velocity as a function of displacement. What is telling you how fast are you going? This is actually velocity square dotted with itself. It's telling you how fast you're going after having traveled this distance. Okay. All right, this goes through the derivation. I won't go through that. Okay, so a freely falling object, what this means is a freely falling object means an object that is falling under the influence of gravity alone. Okay, that means air resistance is negligible and so on. Okay. And the acceleration is a vector pointing that way, and the magnitude of this acceleration is 9.8 meters per second squared, and it's given a special name g, referencing to acceleration due to gravity. Okay. So for instance, if you point your axis that way, g would be minus 9.8 meters per second squared. Okay. If this is the positive direction of the axis, acceleration is acceleration is that, and if your axis is pointing this way, then the acceleration is 9.8 meters per second squared. Okay, the sign just tells you. Okay, the acceleration due to gravity is always a vector pointing downwards, and if your axis is pointing downwards, that's acceleration is positive, and if your axis is pointing upward, then your acceleration is negative. And of course, if you choose to draw your axis this way, well, I mean, we won't get into two-dimensional stuff, but we'll talk about that later. Okay. All right, guys, so that finishes the lecture portion of this chapter. Okay.